this measured capacity compare with expected values from similar materials, and what does it indicate about the material's efficiency in storing and releasing sodium ions? In what way is the average discharge voltage of about 3.3 V versus Na/Na significant in terms of battery performance? And how might maintaining this voltage level contribute to overall energy output and device stability during operation? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What specific role does the Fe-3/Fe redox couple play in driving the electrochemical activity of alpha-NaFeO2? And how does the associated redox reaction facilitate the intercalation and deintercalation of sodium ions within the layered structure of the cathode? How can we interpret the reaction equation linked to the Fe-3/Fe redox process to gain deeper insight into the electron transfer mechanisms and the resulting structural changes during battery cycling? What implications do these findings have for optimizing cathode material design, and in what ways might modifications to the material's composition or synthesis process further improve the capacity and voltage stability? How does the experimental evidence support the understanding of the interplay between redox chemistry and the electrochemical performance? And what further research questions arise regarding the influence of operating conditions on the reversibility of the redox process and long-term cycling stability of this cathode material? What additional tests or characterization techniques could be employed to validate the reaction mechanisms and explore potential strategies for enhancing battery performance while mitigating degradation? How does the cutoff voltage influence the reversibility of the electrode during the charge and discharge processes, and what does figure 3.5a reveal about this dependence? In what way does expanding the voltage range contribute to an improvement in capacity, and what are the underlying mechanisms that allow for this enhancement in performance? Why does the reversible capacity during the cycle begin to decrease significantly when the voltage exceeds 3.5 V, and what factors might be responsible for this degradation? How is the cycle stability affected by an increase in voltage beyond 3.5 V, and what insights can be drawn from the behavior depicted in figure 3.5 B? What chemical or structural changes could be occurring within the electrode material as the voltage increases, and how might these changes impact both the reversibility and the long-term cycling performance? Given that the redox processes and the structural integrity of the electrode are closely linked, how might the imposed cutoff voltage alter the dynamics of these redox reactions and the overall efficiency of alpha-NaFeO2 as a cathode material? What?